When we picture the universe, we usually imagine things: stars, galaxies, glowing gas, massive black holes. But on the larger scales, the dominant feature of the universe isn't stuff. It's absence. Astronomers have discovered regions so vast and so underpopulated that they make intergalactic space elsewhere look crowded by comparison. These regions aren't small gaps between galaxies. They're enormous volumes, hundreds of millions of light-years across, where almost nothing formed. No galaxy clusters. Very few stars. Hardly any matter at all. What makes this strange isn't just their size, it's that the universe wasn't supposed to arrange itself this way so dramatically. After the Big Bang, matter started out almost evenly distributed. Tiny differences in density slowly grew under gravity. Over billions of years, those small differences turned into the cosmic web we see today. Dense filaments and clusters surrounding vast empty regions called voids. Some voids are modest, others are extreme. A few are so large that if you were inside one, the nearest major galaxy cluster would be unimaginably far away. These are the largest empty spaces we know of, places where gravity, dark matter, and cosmic expansion all pulled matter outward instead of pulling it in. Going inside one of these voids forces us to rethink what empty really means, how structure forms, and how much of the universe is shaped not by what exists, but by what never did. Let's step inside the largest emptiness we know. When astronomers say a region of space is empty, they don't mean empty the way we mean an empty room. Even the most barren regions of the universe still contain matter, radiation, and structure. The word void is a technical label, not a literal description. To understand the largest empty space in the universe, we first have to reset what emptiness actually means on cosmic scales. Start with everyday intuition. If you drift far from Earth, past the planets, past the sun's influence, space already feels empty. The density of matter drops fast. Interplanetary space has only a handful of particles per cubic centimeter. Interstellar space inside galaxies is thinner still. Intergalactic space between galaxies is even more rarefied. By the time you're between galaxy clusters, you're dealing with densities so low that calling them vacuum feels reasonable. But cosmology doesn't work with intuition. It works with averages. On the largest scales, astronomers measure how matter is distributed relative to the cosmic mean. That mean includes everything: stars, gas, dust, dark matter, and even the faint background radiation left over from the early universe. A cosmic void is defined not by the absence of matter, but by a significant deficit compared to that average. In practice, a void is a region where the matter density is typically 10 to 20% of the cosmic mean, sometimes even lower. That means 80 to 90% of the matter you'd expect simply isn't there. It has flowed elsewhere over billions of years. That's what makes voids remarkable. Not that they're empty, but that they're missing so much. This definition matters because the universe taken as a whole is remarkably uniform. On very large scales, matter is spread out almost evenly. The deviations that exist are small in absolute terms. Even galaxy clusters, the densest large structures, are only slight over-densities compared to the cosmic average. Voids are the opposite side of that same coin, regions where those small early differences compounded in the other direction. Another crucial point: when astronomers talk about voids, they are almost always talking about galaxies first, not matter directly. Galaxies are what we see. They are the tracers. When surveys map the universe, they're mapping where galaxies are located, how many there are in a given volume, and how they cluster together. Voids are initially identified as regions with very few or no galaxies above a certain brightness. This introduces an important subtlety. A region can look empty in galaxies but still contain dark matter and gas. In fact, it always does. Dark matter makes up most of the universe's matter content, and it does not emit light. It forms a web of invisible structure that galaxies grow inside. Even in the deepest voids, dark matter is present. It's just more spread out. The same goes for diffuse gas, mostly hydrogen and helium, left over from the early universe. The gas density in voids is extremely low, but it never drops to zero. So when you hear largest empty space, what you should picture is not a hole punched through reality, but a vast, underdeveloped region of the cosmic web. It's a place where structure formation barely got started. To see why this distinction matters, It helps to go back to the early universe. After the Big Bang, matter was distributed almost perfectly evenly. The variations in density were tiny, differences of about 1 part in 100,000. Those fluctuations were enough. Gravity amplified them over time. Slightly denser regions pulled in more matter and grew denser still. Slightly emptier regions lost matter to their surroundings and became emptier. This process didn't create isolated islands of matter floating in nothingness. It created a connected network. Matter flowed along preferred directions, forming filaments and sheets. Where filaments intersected, galaxy clusters formed. Where matter flowed away, voids opened up. In this picture, voids are not gaps left behind accidentally. They are active participants in the universe's evolution. Matter doesn't just sit still and fail to form galaxies there. It actively moves out. That's why voids expand faster than the universe's average expansion. Inside a void, there's less gravity pulling matter back together. The local expansion rate is slightly higher. Over billions of years, this causes voids to grow larger and emptier relative to their surroundings. Now consider scale. A small cosmic void might be 20 or 30 million light-years across. Even that dwarfs individual galaxies. Larger voids can reach 100 million light-years or more. The largest known voids are hundreds of millions of light-years across. At that scale, the idea of emptiness stops being intuitive entirely. Another thing cosmologists mean by empty is dynamically quiet. In dense regions, galaxies interact constantly. They merge, collide, strip gas from each other, and trigger bursts of star formation. In voids, those interactions are rare. Galaxies evolve slowly and in isolation. Many are small, faint, and irregular. Some may have barely changed for billions of years. So emptiness also means inactivity, fewer gravitational encounters, fewer dramatic events, a slower pace of cosmic evolution. There's also a statistical meaning to emptiness. Voids are not defined by sharp boundaries. There is no wall where density suddenly drops to zero. Instead, density gradually decreases as you move inward from filaments toward the center of a void. Astronomers use algorithms to define where a void begins and ends based on thresholds, how underdense a region is compared to the average. Different definitions produce different void catalogues. Some methods focus on spherical regions with minimal galaxy counts. Others identify irregular shapes based on the topology of the cosmic web. This is why the largest void depends slightly on how you define it. The emptiness is real, but the edges are fuzzy. This fuzziness is another reason emptiness in cosmology is not absolute. Voids overlap. They merge, they contain subvoids. A large void can contain smaller, even emptier regions inside it. The universe is hierarchical in its emptiness, just as it is in its structures. There's one more layer to what empty means, and it's often overlooked: radiation and fields. Even the emptiest voids are filled with the cosmic microwave background, the afterglow of the Big Bang. Every cubic centimeter of space contains about 400 photons from that background radiation. Neutrinos stream through voids almost without interacting. Gravitational fields pass through. Space itself has structure and curvature. So from a fundamental physics perspective, emptiness doesn't exist at all. There is no region of the universe that lacks physical content entirely. What makes cosmic voids special is not the absence of everything, but the absence of complexity. They are places where the universe failed to build much of anything interesting, at least by the standards we usually care about. This reframing is essential before talking about the largest voids specifically. Otherwise, it's easy to fall into the trap of imagining them as mysterious holes or anomalies. They're not. They are a natural, expected outcome of the same processes that built galaxies and clusters. In fact, in many ways, voids are cleaner laboratories for cosmology than dense regions. Dense regions are messy. They involve nonlinear physics, star formation, supernova, black hole feedback, turbulence, and magnetic fields. Voids are simpler. Gravity dominates. Expansion dominates. The initial conditions are preserved more clearly. That's why cosmologists are so interested in emptiness. Voids retain memory. When we say inside the largest empty space in the universe, what we really mean is inside the most extreme example of this underdevelopment, a region where matter was just slightly less dense at the beginning, and that small disadvantage compounded over 13.8 billion years into near isolation. So from here on, whenever empty comes up, keep this definition in mind. Empty does not mean nothing. It means far less than average. It means matter has been pushed aside. It means gravity lost the competition there. And with that clarified, we can zoom out and look at how these vast empty regions fit into the overall architecture of the universe itself. To understand where the largest empty spaces come from, you have to stop thinking about the universe as a random scatter of galaxies and start thinking about it as an organized system, not organized by intention but by physics. On the larger scales, the universe has a structure, and that structure explains why emptiness ends up being such a dominant feature. Astronomers call this structure the cosmic web. It's not a metaphor meant to sound dramatic. It's a literal description of what galaxy surveys reveal when you map millions of galaxies in 3 dimensions. Matter is not spread evenly. It's arranged in long filaments, broad walls, dense knots, and vast gaps in between. Those gaps are the voids. This pattern didn't emerge recently. It's been developing for almost the entire age of the universe. Right after the Big Bang, the universe was hot, dense, and extremely uniform. But uniform doesn't mean perfectly smooth. Tiny fluctuations existed from the beginning. Some regions were very slightly denser than others. The differences were incredibly small, but gravity doesn't need much to get started. Given enough time, it amplifies whatever differences exist. As the universe expanded and cooled, matter began responding to those initial variations. Where density was slightly higher, gravity pulled matter inward. Where density was slightly lower, matter flowed outward toward denser regions. This process happened everywhere at once, across all scales, and it never really stopped. Over time, this led to a self-reinforcing pattern. Dense regions became denser. Empty regions became emptier. But the geometry matters. Matter doesn't collapse inward equally from all directions. It flows along preferred paths defined by the initial density field. First, matter collapses into sheets. Then those sheets collapse into filaments. Finally, filaments intersect to form dense nodes, galaxy groups, and clusters. This sequence is sometimes called anisotropic collapse. The key idea is that gravity acts more strongly along certain directions than others, depending on how matter is distributed nearby. The result is not a collection of spherical blobs, but a network. Imagine stretching a sponge and then letting parts of it collapse while others stretch further. The material collects along ridges and intersections, leaving cavities in between. That's roughly what gravity does to matter on cosmic scales. The filaments of the cosmic web are enormous. They can be hundreds of millions of light-years long. Along them, galaxies are strung out like beads. Gas flows along these filaments, feeding star formation and black hole growth. Dark matter provides the gravitational backbone that holds everything together. Where multiple filaments intersect, clusters form. These are the densest large structures in the universe. They contain hundreds or thousands of galaxies bound together by gravity, embedded in massive halos of dark matter, filled with hot gas that glows in X-rays. Between the filaments and clusters lie the voids. Voids are not accidental leftovers. They are integral parts of the web. In fact, the cosmic web is often better defined by its empty spaces than by its dense ones. If you remove the galaxies from a large-scale map and only look at the empty regions, you still recover the same structure, just inverted. One way to think about it is that voids are the expanding regions and filaments are the compressed regions. The universe's expansion stretches space everywhere, but gravity locally counteracts that expansion where matter is dense. In underdense regions, there's less gravity to slow things down, so expansion wins more easily. As a result, voids expand faster than average. Over billions of years, they grow larger relative to the rest of the universe. Filaments and clusters, meanwhile, grow by accreting matter from their surroundings, including matter that drains out of voids. This creates a feedback loop. As voids lose matter, they become even less gravitationally attractive. As filaments gain matter, they become more attractive. The contrast sharpens. Importantly, this process is scale-dependent. On very small scales, physics like gas pressure, radiation, and feedback from stars and black holes complicate things. On very large scales, gravity dominates and the behavior becomes simpler and more predictable. That's why the cosmic web looks similar in simulations and observations. When cosmologists run large-scale simulations, starting from the measured conditions of the early universe, the same web-like structure appears naturally. No tuning is required. Voids form automatically. Another key feature of this organization is hierarchy. There is no single-size scale for voids, filaments, or clusters. Small voids exist within larger voids. Thin filaments connect to thicker ones. Galaxy groups sit inside larger superclusters. This hierarchy comes directly from the spectrum of initial fluctuations. The early universe contained density variations on many different scales. Small fluctuations collapsed first, forming small structures. Larger fluctuations took longer to grow but eventually shaped the largest features we see today. So when we talk about the largest empty spaces, we are talking about the largest scale underdensities that survived and grew over cosmic time. These are not anomalies layered on top of the cosmic web. They are its largest components. There's also an important observational angle here. The cosmic web is not something we see directly in a photograph. It's reconstructed statistically from galaxy surveys. Astronomers measure the positions and redshifts of millions of galaxies, then infer the three-dimensional structure of the universe. When you plot those positions, the web becomes obvious. Galaxies cluster along lines and surfaces. Large regions contain almost none. Those regions are the voids. But the web is not static, it evolves. At earlier times, the contrast between dense and empty regions was smaller. As the universe aged, the web sharpened. Voids became emptier. Filaments became denser. Clusters became more massive. This evolution is slow on human timescales, but dramatic over billions of years. The largest voids we see today were much less empty in the past. They contained more matter, more gas, and more small structures. Over time, much of that material flowed outward. Dark matter plays a central role in this organization. Because it interacts almost exclusively through gravity, it responds cleanly to the initial density field. It forms the scaffolding of the cosmic web. Ordinary matter, gas and stars, follows that scaffolding but with additional physics layered on top. In voids, dark matter density is low but not zero. The dark matter there forms shallow potential wells. Gas has trouble cooling and collapsing in those environments. As a result, galaxy formation is inefficient. This is why voids contain so few galaxies and why the galaxies they do contain tend to be small and isolated. Another consequence of this organization is that voids are typically surrounded by walls and filaments. Matter doesn't just leave a void randomly. It flows towards specific structures. This gives voids a kind of boundary, even if it's not sharp. From inside a large void, the universe would look very different. Galaxies would be few and far between. The sky would be darker. Most of the mass would lie far away, concentrated along distant filaments and walls. Yet even from inside a void, the cosmic web would still exist. It would just be farther out. One subtle but important point is that the cosmic web is not imposed on the universe by expansion. Expansion stretches everything uniformly. Structure comes from gravity acting on initial conditions. Voids are not places where expansion somehow won by itself. They are places where gravity lost because there wasn't enough matter there to fight back. This distinction matters when thinking about the limits of structure. The largest voids are not arbitrary. Their sizes reflect the scale of the largest initial underdensities and the amount of time gravity has had to amplify them. If voids were much larger than we observe, it would challenge our understanding of the early universe. This is why cosmologists care deeply about mapping the largest empty regions accurately. They are direct probes of the initial conditions set shortly after the Big Bang. So when you zoom out far enough, the universe stops looking like a collection of galaxies and starts looking like a pattern of emptiness punctuated by structure. The emptiness isn't a background, it's part of the design. With that framework in place, the cosmic web, its filaments, clusters and voids, we can now look at how astronomers first realized that some of these empty regions weren't just small gaps, but enormous volumes where something fundamental was missing. The idea that the universe contains vast empty regions wasn't obvious at first. For much of the 20th century, astronomers assumed that on large scales, galaxies were spread out more or less uniformly. Clusters were known, of course, but they were treated as local features, sitting on top of an otherwise smooth background. The possibility that enormous volumes of space might contain almost nothing simply wasn't part of the standard picture. That changed when astronomers started mapping the universe in 3 dimensions instead of 2. Early galaxy catalogues were flat. They showed where galaxies appeared on the sky, but not how far away they were. In those maps, galaxies seemed scattered somewhat unevenly, but depth was missing. Without distance information, it was impossible to tell whether apparent gaps were real or just lines of sight with fewer galaxies. The breakthrough came with redshift surveys. By measuring how much a galaxy's light is stretched by cosmic expansion, astronomers can estimate its distance. In the 1970s and early 1980s, technology finally made it practical to measure redshifts for large numbers of galaxies. Instead of dots on a sky map, astronomers could now place galaxies in three-dimensional space. When they did, the universe started to look very different. One of the earliest hints came from narrow slice surveys. Astronomers would take a thin wedge of the sky and measure redshifts for every galaxy within it. When these slices were plotted, galaxies didn't fill the volume evenly. They lined up along arcs, chains, and walls. Between them were regions with almost nothing. At first, these empty regions were treated cautiously. The surveys were limited. Selection effects were everywhere. Maybe astronomers were missing faint galaxies. Maybe the gaps were artifacts of incomplete data. But as surveys improved and expanded, the pattern didn't go away. It became clearer. One of the most influential moments came in the early 1980s with the publication of detailed redshift maps showing what later became known as the bubble or foam-like structure of the universe. Galaxies appeared to trace the surfaces of large, roughly spherical regions. The interiors of those regions were strikingly underpopulated. This was not what many cosmologists expected to see. At the time, theoretical models of structure formation were still being refined. The idea that gravity could produce filaments and walls was gaining traction, but the sheer emptiness of the voids was surprising. Some of these regions were tens of millions of light-years across and contained very few galaxies brighter than the survey limits. Then came the discovery that made it impossible to dismiss voids as minor features. In 1981, astronomers studying galaxy distributions identified a region in the direction of the constellation Boötes that appeared almost completely empty. This region, later called the Boötes Void, was enormous, roughly 250 million light-years in diameter. At the time, it was the largest known structure of its kind. To put that in perspective, the Milky Way is about 100,000 light-years across. The Boötes Void was thousands of times larger. What shocked astronomers wasn't just the size, it was how few galaxies were found inside it. Early surveys detected only a handful, where hundreds or thousands would have been expected if galaxies were distributed evenly. This forced a reckoning. Either the surveys were fundamentally flawed, or the universe really did contain regions that empty. Astronomers responded the only way they could, by looking harder. Deeper surveys were conducted. Fainter galaxies were searched for. Different wavelengths were used to make sure dust or selection bias wasn't hiding large populations. The void remained. Over time, a small number of galaxies were found inside it, but that only sharpened the conclusion. The Boötes Void wasn't empty in an absolute sense, but it was dramatically underdense. It was real. This discovery didn't stand alone for long. As redshift surveys expanded, more voids appeared. Some were smaller, some comparable in size. The universe began to look less like a smooth distribution with a few clusters and more like a network of dense regions surrounding enormous empty volumes. Importantly, these discoveries didn't come from one team or one instrument. Different surveys using different telescopes and methods found the same general pattern. That convergence mattered. It meant voids weren't an observational illusion. The reaction within the cosmology community was mixed at first. Some researchers had already been developing models that predicted large-scale structure with voids. Others were more skeptical, worried that the interpretation was getting ahead of the data. One source of concern was bias. Galaxies are not perfect tracers of matter. Bright galaxies might avoid certain environments, even if dark matter is present. So could these voids be regions with matter but no luminous galaxies? This question drove a lot of follow-up work. Astronomers looked for gas using radio observations, especially neutral hydrogen. They looked for faint dwarf galaxies. They compared observations with simulations that included both dark matter and galaxy formation. What emerged was a consistent picture. Voids were underdense in dark matter as well, not just in visible galaxies. The galaxy deficit was real, but it reflected an underlying mass deficit. Another key development was the realization that voids are not rare anomalies. They occupy most of the universe's volume. Dense regions like clusters and filaments contain most of the mass, but they take up relatively little space. Voids, by contrast, contain little mass but dominate the volume. Depending on how you define them, voids make up roughly 70 to 80% of the observable universe's volume. This flipped intuition on its head. The typical place in the universe is not inside a galaxy or near a cluster. It's inside a void. As surveys grew larger, astronomers began cataloguing voids systematically. This required new tools. You can't identify voids by eye once you're dealing with millions of galaxies. Algorithms were developed to find underdense regions, characterize their sizes and shapes, and study their statistical properties. These efforts revealed that voids follow patterns of their own. Their size distribution, shapes, and spatial correlations matched what cosmological models predicted from the initial conditions of the universe. This was a crucial validation of the emerging standard model of cosmology. The discovery of voids also changed how astronomers interpreted older observations. Features that once seemed puzzling or inconsistent started to make sense in the context of a web-like universe with large empty regions. It also influenced how new surveys were designed. Instead of focusing only on dense regions, astronomers began deliberately mapping large volumes to capture the full structure, including emptiness. There was another, more subtle shift as well. Voids stopped being treated as embarrassing gaps in data and started being treated as valuable data themselves. Dense regions are complicated. Many physical processes overlap and interfere with each other. Voids are simpler. The physics is cleaner. This makes them powerful tools for testing cosmological models, especially those involving dark matter and dark energy. All of this traces back to those early discoveries when astronomers first realized that something fundamental was missing from large regions of space. What's striking in hindsight is how late this realization came. The universe is nearly 14 billion years old. Galaxies have been forming for most of that time. Yet it took until the late 20th century, with the right combination of technology and perspective, for humans to notice that the dominant feature of the cosmos is emptiness. Once seen, it couldn't be unseen. By the end of the 1980s and into the 1990s, the existence of cosmic voids was no longer controversial. The focus shifted from "do they exist?" to "how do they work?" and "what can they tell us?" And answering those questions required better maps. To understand how astronomers identify, measure, and define the largest empty spaces today, we need to look at the tools they use to find something that, by definition, barely shows up at all. Finding something by looking for what isn't there sounds simple, but in astronomy, it's one of the hardest tasks. You can't point a telescope at emptiness and measure it directly. You have to infer it from patterns, statistics, and absence. That's exactly the challenge astronomers face when they try to detect and map cosmic voids. Everything starts with galaxies. Galaxies are bright. They're visible across vast distances. More importantly, they trace where matter has successfully collapsed and formed structure. Astronomers use galaxies as markers, the same way you might infer the shape of a city by looking at where streetlights are clustered. The dark areas between them tell a story. The primary tool for this is the redshift survey. In a redshift survey, astronomers measure two things for each galaxy: its position on the sky and how much its light has been stretched by the expansion of the universe. That stretch, called redshift, provides an estimate of distance. Put those together for millions of galaxies and you get a three-dimensional map of where galaxies are located in space. Modern surveys cover enormous volumes. They don't just look deep in one direction. They tile large areas of the sky and extend billions of light years outward. When those data are plotted, voids reveal themselves naturally as regions where galaxy counts drop sharply. But seeing a sparse region is not the same as defining a void. Galaxies are discrete objects. They're points, not a continuous fluid. Even in a perfectly uniform universe, you'd expect random gaps simply due to chance. The challenge is separating real, physically meaningful underdensities from statistical noise. This is where void-finding methods come in. The simplest approach is galaxy counting. Astronomers divide space into volumes of a chosen size and count how many galaxies fall inside each one. Regions with significantly fewer galaxies than average are flagged as underdense. This method is intuitive, but it depends heavily on choices: the size of the volume, the brightness cutoff for galaxies, and the survey's completeness. More sophisticated methods go beyond simple counting. One widely used approach involves finding the largest empty spheres that can be placed among galaxies. You start by identifying points in space that are far from any galaxy, then grow spheres outward until they touch surrounding galaxies. These maximal empty spheres define candidate voids. Overlapping spheres can be combined to define larger, irregularly shaped void regions. Another class of methods looks at the topology of the galaxy distribution. Instead of asking where galaxies are absent, these methods analyze how the density field changes across space. They identify ridges, valleys, and basins in the matter distribution. Voids correspond to basins, regions where density is locally minimal. This approach treats the universe more like a landscape than a scatterplot. Dense regions are mountains, filaments are ridges, voids are valleys. Algorithms trace how matter would flow downhill under gravity and identify the catchment areas of these flows. Those catchment areas are voids. This landscape-based view aligns well with how voids form physically, making it especially useful for comparing observations with simulations. But there's a complication. Surveys don't observe matter directly. They observe light. And light comes with biases. Brighter galaxies are easier to detect at large distances. Fainter galaxies drop out of surveys as you look farther away. Dust, observational limits, and selection criteria all shape which galaxies make it into a catalogue. If you're not careful, these effects can create artificial voids or hide real ones. To deal with this, astronomers impose strict cuts on their data. They define volume-limited samples, where only galaxies above a certain brightness are included, ensuring that the sample is complete out to a given distance. This sacrifices some data but avoids misleading patterns. They also use mock catalogues. Cosmological simulations produce virtual universes with known properties. By applying the same observational limitations to these simulations that real surveys have, astronomers can see how voids should appear in data. This helps calibrate void-finding algorithms and identify biases. Another layer of complexity comes from redshift distortions. Redshift measures distance through cosmic expansion, but galaxies also have their own motions. They fall toward clusters, orbit within groups, and stream along filaments. These motions distort the apparent positions of galaxies in redshift space. In dense regions, this creates elongated structures along the line of sight, sometimes called fingers of God. In voids, the effect goes the other way. Galaxies tend to move outward as voids expand, slightly stretching voids along the line of sight. If not corrected for, these distortions can change the apparent shapes and sizes of voids. Modern analyses model these effects explicitly, allowing astronomers to recover the true underlying structure. Despite all this complexity, the basic result is robust. Large underdense regions exist, and their properties can be measured consistently across different surveys and methods. Once voids are identified, astronomers measure several key properties. Size is the most obvious, but size itself is tricky. Voids are not perfect spheres. Some are elongated. Some have complex shapes with indentations and protrusions where filaments intrude. Researchers often quote an effective radius, the radius of a sphere with the same volume as the void. Density is another crucial property. This includes both galaxy density and inferred matter density. Voids vary widely. Some are mildly underdense. Others are extreme, with matter densities less than 10% of the cosmic average in their centers. Shape matters too. Voids tend to be somewhat elongated, reflecting the anisotropic nature of structure formation. Their orientations can correlate with nearby filaments and walls, providing clues about how matter flows on large scales. There's also the concept of void hierarchy. Small voids can exist within larger ones. A region that looks empty at one scale may contain structure at a smaller scale. Void catalogues often capture this nesting, allowing astronomers to study how emptiness itself is organized. As surveys improved, void catalogues exploded in size. Instead of a handful of famous voids, astronomers now work with tens of thousands identified across the observable universe. This statistical power transformed voids from curiosities into precision tools. One reason voids are so valuable is that they're sensitive to cosmology in ways dense regions are not. The way voids grow, merge, and distort over time depends on the properties of dark matter, the amount of dark energy, and the overall geometry of the universe. This makes accurate void measurement critical. Small errors in defining void boundaries can propagate into large uncertainties in cosmological conclusions. That's why void finding remains an active area of research with constant refinement of methods. There's also a philosophical shift embedded in this work. Traditional astronomy focused on objects, stars, galaxies, clusters. Void science focuses on relationships and patterns. It treats the universe as a continuous system shaped by underlying fields, not just a collection of luminous points. Perhaps the strangest aspect of all this is that the largest voids are often easier to find than smaller ones. Their scale makes them stand out statistically. Random fluctuations rarely produce such vast empty regions. When you see one spanning hundreds of millions of light-years, it's almost certainly physical. This brings us back to the largest empty spaces in the universe. Identifying them requires not just powerful telescopes, but careful definitions and massive datasets. Their existence is not obvious from any single observation. It emerges only when you step back far enough and let patterns speak. With these tools in hand, astronomers were finally able to characterize individual giant voids in detail, and one of the first, and still one of the most famous, set the benchmark for what empty could really mean on cosmic scales. When astronomers first identified the Botas void, it didn't just add another data point to the growing list of cosmic voids, it reset expectations. Until then, emptiness had been measured in tens of millions of light-years. This was something else entirely. The Botas void lies in the direction of the constellation Botas, roughly 700 million light-years away from Earth. What immediately stood out wasn't its location, but its scale. Early measurements suggested a diameter of about 250 million light-years. Even today, depending on how its boundaries are defined, estimates remain in that same range. At the time of its discovery in the early 1980s, this made it the largest known underdense region in the universe. To understand why this was so unsettling, it helps to remember the state of cosmology then. Large-scale structure was still being mapped for the first time. Filaments and walls were only beginning to emerge from redshift surveys. The idea that a single region could span hundreds of millions of light-years and contain almost nothing pushed models to their limits. The Botas void wasn't identified because astronomers were specifically looking for something that large. It revealed itself as surveys expanded and gaps became impossible to ignore. In galaxy slice maps, it appeared as a yawning hole, an area where galaxies simply stopped showing up. Initial reactions were cautious. A region that large with so few galaxies could easily be a selection effect. Maybe surveys weren't deep enough. Maybe dust obscuration was hiding galaxies. Maybe the void wasn't real at all. So astronomers went back and checked. They looked deeper, including fainter galaxies. They used different instruments and different wavelengths. They mapped the region repeatedly. Each time, the same result appeared. The Botas region was dramatically underpopulated. Even after decades of follow-up observations, only a few dozen galaxies have been identified inside the void, far fewer than expected for a region of that size. These galaxies are not evenly distributed either. They tend to sit in small, isolated groups or along faint internal filaments, leaving the central regions extraordinarily empty. This wasn't just a statistical fluctuation. It was a genuine feature of the cosmic web. What made the Botas void especially striking was its isolation. Many voids are parts of a complex network, merging into one another or bordered by multiple large filaments. Botas, by contrast, appeared unusually clean and well-defined, surrounded by walls and filaments of galaxies that emphasized its emptiness. From a visualization standpoint, it looked almost like a bubble carved out of the universe. That visual impression was powerful, but the physics behind it mattered more. The existence of such a large void raised immediate questions about structure formation. How could gravity, starting from tiny initial fluctuations, produce something so vast and so empty without breaking the statistical rules set by the early universe? The answer, it turned out, was that it could, but only just. In cosmological models based on the observed initial conditions of the universe, very large voids are rare but not forbidden. They represent the extreme tail of the distribution, regions where initial density was unusually low across a very large volume. Over billions of years, that small disadvantage compounded into dramatic emptiness. The Botas void became a test case. If models couldn't reproduce something like it, those models would be in trouble. Simulations rose to the challenge. As computational power increased and simulations grew in volume, voids comparable to botas began to appear naturally, though infrequently. This was an important validation. It showed that the void didn't require exotic physics or special conditions. It was an extreme but expected outcome. Still, expected doesn't mean common. Even today, voids as large and as empty as botas are unusual. Many later discovered voids rival its size, and some exceed it depending on definition, but botas remains historically important because it forced cosmologists to confront the reality of extreme emptiness early on. Another reason the botas void mattered is that it shifted attention away from just size and toward internal structure. At first glance, the void seemed almost completely empty, but deeper observations revealed that it wasn't a featureless nothing. It contained a sparse population of galaxies, many of them small, faint, and gas-rich. These galaxies tended to be isolated, with few neighbours and little evidence of past interactions. This fit well with emerging ideas about void galaxy evolution. In dense environments, galaxies are constantly influenced by their surroundings. In voids, they evolve slowly, shaped mostly by their own internal processes rather than external forces. Some galaxies inside the botas void show signs of ongoing star formation despite their isolation. Others appear relatively pristine with low metallicity, suggesting they haven't undergone many cycles of starbirth and death. In that sense, the void acts as a kind of cosmic time capsule. But the most extreme aspect of the botas void isn't what's inside it, it's how matter behaves around it. The void is surrounded by a network of filaments and walls that contain a much higher density of galaxies. Matter has flowed out of the void over cosmic time and accumulated along these surrounding structures. This creates a sharp contrast between the interior and the edges. In simulations, this process is clear. Matter drains out of underdense regions and piles up at their boundaries. The larger the void, the more pronounced this effect becomes. Botas represents an advanced stage of this process. From the perspective of gravity, the void acts almost like a repulsive region, not because gravity pushes things away, but because there's so little mass inside that surrounding regions pull matter outward. The result is an effective evacuation. This evacuation has consequences for motion as well as distribution. Galaxies near the edges of large voids experience peculiar velocities as they move away from the void interior and toward denser regions. These motions can be measured statistically and used to infer the underlying mass distribution. In that sense, the botas void is not just a passive absence. It actively shapes the dynamics of nearby galaxies. There was also a period when some researchers speculated whether such a large void could have observable effects on cosmological measurements. Could living near a large void alter the apparent expansion rate of the universe? Could it bias observations of distant galaxies? These ideas were explored seriously. Some alternative cosmological models proposed that if we lived inside a sufficiently large void, it might mimic the effects attributed to dark energy. The botas void, however, was far too small and too distant to support such ideas. But it helped motivate careful studies of how voids affect observations. Another important role of the botas void was methodological. Because it was such a clear and dramatic example, it became a benchmark for testing void-finding algorithms. Any method claiming to identify large voids had to be able to recover botas reliably. In this way, a single empty region influenced how astronomers studied emptiness more broadly. As larger and deeper surveys came online in the following decades, more voids were discovered, some comparable in size, others larger but less extreme in density. Yet botas retained a special status. It was the first time astronomers had to seriously grapple with the idea that the universe could contain a region hundreds of millions of light-years across where structure formation had almost completely failed. There's also a psychological aspect to its impact. Dense structures are intuitive. We expect matter to clump. Emptiness on that scale feels wrong, even when equations say it's allowed. Botas forced a shift in intuition. It also changed how astronomers talked about the universe to the public and to each other. Instead of emphasizing galaxies and clusters alone, discussions increasingly included voids as equally important components of cosmic structure. Over time, botas became less of an anomaly and more of a reference point. As new surveys mapped larger volumes, astronomers realized that the universe contains a wide range of void sizes and densities. Botes sits near the extreme end, but it's part of a continuum, not a singular oddity. Still, its discovery remains a turning point. It showed that the largest structures in the universe are not necessarily things, but absences. It demonstrated that gravity, given enough time, can carve out vast regions where almost nothing happens. And it highlighted the importance of studying not just where matter is, but where it isn't. As impressive as the Boötes void is, it's not the final word on cosmic emptiness. Later observations would reveal even larger underdense regions and new connections between voids and other cosmic phenomena. One of those connections involves an unexpected feature in the cosmic microwave background, a cold patch of sky that some researchers think may be linked to a giant void. To understand that possibility, we have to move from Boötes to another region of the universe, and from galaxy surveys to the faint afterglow of the Big Bang itself. Long after the Boötes void reshaped how astronomers thought about emptiness, a very different kind of observation reopened the conversation, this time using the oldest light in the universe instead of galaxies. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang. It fills all of space and looks almost perfectly uniform in every direction. Almost, but not quite. Tiny temperature variations, differences of a few tens of microkelvin, encode information about the early universe and the large-scale structure that formed later. In the early 2000s, when detailed CMB maps became available, astronomers noticed something strange. There was a patch of sky in the direction of the constellation Eridanus that was significantly colder than average, not dramatically so, but enough to stand out statistically. This feature became known simply as the cold spot. At first, the cold spot was treated as a curiosity. Random fluctuations are expected in the CMB. Given enough sky, something unusual will always show up somewhere. But as data improved and the feature persisted, it became harder to dismiss. The cold spot is large. Depending on how you define it, it spans several degrees on the sky. That corresponds to a physical size of hundreds of millions of light-years at cosmological distances. Its temperature depression is also deeper than typical fluctuations of the same scale. This raised a question that cosmologists take seriously. Is this just an unlikely fluctuation, or is something in the universe between us and the CMB affecting what we see? One proposed answer brought cosmic voids back into focus. When light travels through the universe, it doesn't just move through empty passive space. It passes through gravitational fields created by matter. In dense regions, gravity can slightly boost the energy of photons. In underdense regions, the opposite can happen. This effect is subtle, but over enormous distances, it can add up. In an expanding universe dominated by dark energy, this process becomes asymmetric. A photon entering a large void loses a bit of energy as it climbs out of surrounding gravitational wells. When it exits the void, the universe has expanded slightly and the gravitational potential has changed. The photon doesn't fully regain what it lost. The net result is a small drop in energy, a slight cooling. This mechanism is known as the integrated Sachs-Wolf effect. It's real, measured, and expected. The question is whether it can explain something as prominent as the cold spot. To test this idea, astronomers looked for large underdense regions along the line of sight to the cold spot. If a massive void lay between us and the surface of a last scattering, it could, in principle, imprint a cold region onto the CMB. What they found was intriguing. Galaxy surveys revealed an extended underdense region in roughly the same direction as the cold spot. This region came to be called the Eridanus supervoid. Estimates of its size vary, but it appears to span several hundred million light-years and to be significantly underdense compared to the cosmic average. At first glance, this seemed like a promising explanation. A large void aligned with the cold spot, affecting ancient light through known physics. It fit neatly. But cosmology rarely offers simple answers. The first complication is size. To produce a temperature decrement as large as the cold spot through the integrated Sachs-Wolf effect alone, the void would need to be exceptionally large and deep. Larger and emptier than what most observations suggest the Eridanus supervoid actually is. Some analyses argued that the void is not a single coherent structure, but a line of sight alignment of smaller voids at different distances. This kind of stacking can enhance observational signals without representing one enormous empty region. If that's the case, its effect on the CMB would be weaker than required. Another complication is statistics. Even if the void contributes to the cold spot, it may not account for all of it. Part of the signal could still be a primordial fluctuation, a rare but a loud feature imprinted at the very beginning of the universe. This leads to a hybrid picture. The cold spot may be partly primordial and partly enhanced by intervening structure. In this view, the void doesn't create the anomaly from scratch. It deepens an existing one. There's also the issue of alignment. The universe is large. Given enough features, some alignments will happen by chance. The fact that a void and a cold region overlap on the sky doesn't automatically imply causation. Careful statistical analysis is needed to determine whether the alignment is more than coincidence. Over the years, studies have gone back and forth on this. Some find that the Eridanus supervoid can explain a non-negligible fraction of the cold spot signal. Others find that its contribution is too small to matter much. What's important is that this debate didn't hinge on speculation or exotic physics. It relied on measurable structures, well-understood gravitational effects, and increasingly precise data. Regardless of the final answer, the cold spot void connection had a major impact. It demonstrated that voids are not just passive regions defined by absence. They can influence observations across cosmic time. A structure that formed billions of years after the Big Bang can subtly modify light that's been traveling for almost the entire age of the universe. It also highlighted the scale of the largest underdense regions. The fact that a void large enough to even be considered as an explanation exists at all speaks to how extreme cosmic emptiness can be. The Eridanus supervoid, like Bota's before it, occupies the upper end of the void size distribution. It's not representative of typical voids. It's a rare structure formed from an unusually large initial underdensity. But rare doesn't mean impossible. Another lesson from this episode is methodological. It showed how different cosmic probes, galaxy surveys, and the CMB can be combined to study large-scale structure. Voids are no longer identified only by counting galaxies. They're studied through their gravitational effects, their impact on light, and their role in cosmic evolution. It also tempered expectations. Early excitement sometimes framed the cold spot as evidence for new physics or a breakdown of standard cosmology. As analyses matured, the focus shifted toward more conservative explanations that stayed within known physics. That shift itself is telling. The standard cosmological model is robust enough to accommodate extreme voids, rare fluctuations, and subtle observational effects without collapsing. So where does that leave the cold spot today? It remains unusual. It remains interesting. But it no longer stands as a glaring contradiction. Whether the Eridanus supervoid explains part of it or not, the episode reinforced a broader point. The largest empty regions in the universe are not just empty scenery. They interact with the rest of the cosmos in measurable ways, and they force us to think carefully about scale. A void large enough to leave an imprint on the CMB is operating on scales where the universe transitions from messy, non-linear structure to something closer to the pristine conditions of the early cosmos. Studying such voids pushes cosmology into that boundary regime. As surveys continue to grow and maps improve, the focus has shifted again. Instead of asking whether giant voids exist, astronomers now ask how big they can get and where the true upper limits lie. Because once you accept that voids can span hundreds of millions of light years, the next natural question is unavoidable. Just how big are the largest empty spaces we know of, really? Once astronomers accepted that voids could be enormous, the obvious next step was to quantify just how enormous they could get. Not in vague terms, but in concrete numbers. How big is big when you're talking about the largest empty spaces in the universe? And how do those sizes compare to everything else we know? This is where intuition starts to fail completely. Let's begin with familiar scales and work upward, because jumping straight to the largest voids makes the numbers meaningless without context. A typical large galaxy like the Milky Way is about 100,000 light-years across. Even the largest galaxies rarely exceed a few 100,000 light-years. Galaxy groups, collections of a few dozen galaxies bound together, span a few million light-years. Rich galaxy clusters can reach sizes of 10 to 20 million light-years. Already, these structures dwarf anything we experience directly, but they're still tiny compared to what comes next. Superclusters, loosely connected regions containing many galaxy clusters, can stretch across 100 million light-years or more. Even then, superclusters are not fully gravitationally bound objects. They're transitional features, halfway between structure and the overall expansion of the universe. Now compare that to cosmic voids. A small void in cosmological terms might be 20 to 30 million light-years across. That's already larger than most galaxy clusters. Medium-sized voids commonly reach 50 to 100 million light-years in diameter. These are abundant and form the basic cavities of the cosmic web. But the largest voids are in a different category altogether. Some of the most extreme underdense regions identified in modern surveys have effective diameters of 300, 400, or even 500 million light-years, depending on how they're defined. These are not clean spheres. They're sprawling, irregular volumes shaped by surrounding filaments and walls. But their sheer scale is undeniable. To put that in perspective, light takes 500 million years to cross one of these voids. Entire civilizations could rise and fall many times over before a photon traverses the emptiness. At these scales, voids are no longer just features within the cosmic web. They begin to approach the largest coherent patterns the universe is capable of producing. One famous example often cited is the so-called KBC void, named after the researchers who studied a large local underdensity surrounding our region of the universe. This structure, while still debated in terms of exact size and depth, extends hundreds of millions of light-years and illustrates how large-scale underdensities can exist even relatively nearby in cosmic terms. Other voids identified in large surveys rival or exceed the Bouters void in volume, even if they're less dramatic in terms of central emptiness. This highlights an important distinction. Size and depth are not the same thing. A void can be extremely large but only moderately underdense. Another can be smaller but much emptier in its core. When astronomers talk about the largest voids, they have to specify what they mean. Largest by volume, by diameter, or by deficit of matter. This is why rankings of voids can change as definitions and data improve. Another way to understand the scale is by comparing voids to the observable universe itself. The observable universe has a radius of about 46 billion light-years. That sounds impossibly larger than a 500 million light-year void, and numerically it is. But what matters here is not the absolute size, but the fraction of cosmic structure. The universe does not contain objects approaching its full size. There are no galaxy clusters billions of light-years across. There are no coherent filaments stretching across a significant fraction of the observable universe. Voids are among the largest contiguous regions with a shared physical identity that we can meaningfully define. In other words, voids sit near the upper limit of cosmic structure. This limit exists for a reason. The early universe imposed constraints on how large coherent over- and underdensities could be. Density fluctuations followed a specific statistical distribution, with less power on very large scales. That means extreme features become exponentially rarer as size increases. So while a 30 million light-year void is common, a 300 million light-year void is rare. A billion light-year void would be extraordinary and would likely challenge our understanding of the early universe. This rarity is why claims of extremely large voids are scrutinized carefully. Astronomers ask whether a purported giant void is truly a single structure or whether it's a chain of smaller voids aligned along our line of sight. Projection effects can make separate underdense regions appear connected when they aren't physically coherent. That distinction matters. A real giant void must be underdense in 3 dimensions, not just along a narrow direction. Modern surveys help resolve this by mapping galaxies across wide areas of sky and large depth ranges. With enough data, astronomers can distinguish true large-scale emptiness from chance alignments. Another important comparison is between voids and filaments. Filaments are long but thin. They can stretch hundreds of millions of light-years, but their widths are much smaller. Voids, by contrast, occupy volume. They're the 3-dimensional cavities between filaments. If you were to divide the universe into regions based on volume alone, voids would dominate. They contain most of the space, even though they contain very little of the mass. This leads to a counterintuitive conclusion. The largest structures by volume in the universe are not galaxy clusters or superclusters, but empty regions. And that has consequences. For one thing, it changes how we think about what's typical. The typical environment in the universe is not like our local neighborhood, embedded in a galaxy group near a filament. The typical environment is vastly emptier than that. It also affects how light travels across cosmic distances. Photons spend most of their journey moving through voids. Dense regions are brief interruptions. This matters for subtle effects like gravitational lensing, redshift distortions, and the propagation of background radiation. Another way to grasp void scale is to imagine placing known structures inside one. You could fit the entire local group of galaxies inside a large void and still have tens of millions of light-years of empty space in every direction. You could fit thousands of galaxy clusters inside the volume of the largest voids and barely notice the difference in density. Even the Boötes void, enormous as it is not unique in scale anymore. Later surveys have revealed void complexes, networks of connected underdense regions that rival it in volume, though not always in emptiness. This leads to an important refinement in language. Astronomers increasingly distinguish between voids and supervoids. The latter are extended regions of underdensity that may contain smaller voids and internal structure. The Eridanus supervoid falls into this category. Supervoids challenge simple definitions because they blur the line between individual structures and large-scale trends in the matter distribution. Are they single entities or just regions where multiple voids overlap? The answer depends on scale and purpose. For studying galaxy formation, the distinction may not matter much. For studying cosmology, it matters a great deal. Another key point about size is evolution. Voids grow over time. A void that is 100 million light-years across today was smaller in the past. As the universe expanded and matter flowed outward, voids expanded faster than average. This means the largest voids today represent the accumulated effect of billions of years of expansion and gravitational evacuation. That also means there's a practical upper limit. The universe hasn't had infinite time. There simply hasn't been enough time for arbitrarily large voids to form from realistic initial conditions. Simulations show this clearly. When cosmologists evolve the universe forward from the measured fluctuations in the early universe, void sizes increase steadily but remain bounded. The largest voids at the present epoch fall within a predictable range. This predictability is why void-size distributions are used as cosmological tests. If observations revealed voids systematically larger or emptier than simulations allow, it would signal a problem with our understanding of gravity, dark matter, or the initial conditions of the universe. So far, observations and theory agree reasonably well. That agreement doesn't make the largest voids any less mind-bending. It just makes them comprehensible. There's one more comparison that helps anchor scale: time. The light-crossing time of the largest voids is comparable to the time separating major epochs of cosmic history. A photon entering one side of a giant void might have started its journey when the universe was noticeably younger, with fewer galaxies and less structure overall. In that sense, voids are not just large in space, they span meaningful fractions of cosmic time. And yet, despite their scale, voids are fragile in a way dense structures are not. A small change in initial conditions could erase them or fragment them. They exist because the early universe was just smooth enough, but not too smooth. That balance is what makes the largest empty spaces so informative. Knowing how big voids can get sets the stage for a deeper question. Size tells us how emptiness manifests, but it doesn't tell us what emptiness contains. Because even the largest voids are not truly empty. To understand what's really inside these enormous regions and what makes them physically different from the rest of the universe, we need to look past galaxies and focus on the invisible components that dominate cosmic structure. When you strip away the galaxies, what's left inside a giant cosmic void is easy to underestimate. The absence of bright objects makes it tempting to imagine these regions as almost nothing at all. In reality, voids are filled with components that don't announce themselves loudly, but still shape how the universe works. The most important of these is dark matter. Dark matter outweighs ordinary matter by a factor of about 5, and it's the primary driver of large-scale structure. In voids, dark matter is present everywhere, but at a much lower density than average. Instead of forming deep gravitational wells, it forms shallow, diffuse distributions. Think of the dark matter landscape inside a void as gently rolling terrain rather than sharp valleys. There are no deep pits to trap large amounts of gas. Gravity still operates, but it's weak and spread out. This has immediate consequences. Gas responds to gravity. In dense regions, gas falls into dark matter halos, cools, and forms stars. In voids, the gravitational pull is often too weak to efficiently compress gas. As a result, most of the gas remains diffuse and warm, never reaching the densities required for sustained star formation. That gas is mostly hydrogen and helium, the same elements produced in the Big Bang. Inside voids, it exists as a thin, ionized medium. The density can be so low that there may be fewer than 1 atom per cubic meter in the emptiest regions. That's not a typo. A cubic meter of space can contain less than a single atom on average. Despite that, the total amount of gas in a large void can still be substantial simply because the volume is so enormous. Spread over hundreds of millions of light years, even extremely low densities add up. This gas is not static. It participates in the large-scale flow of matter. Over time, it slowly drifts outward toward the edges of the void, feeding filaments and walls. The process is slow, but over billions of years it reshapes the mass distribution. Along with gas and dark matter, voids are filled with radiation. The cosmic microwave background passes through voids just as it passes through everything else. Every part of space contains those relic photons. Neutrinos produced in vast numbers in the early universe stream through voids almost without interaction. Gravitational waves pass through as well. In terms of fundamental fields and particles, voids are as active as any other region. They are not empty in the sense of lacking physical processes. They are simply low-density environments. Another component that matters is magnetic fields. Magnetic fields in voids are extremely weak compared to those in galaxies or clusters, but they are not necessarily zero. There is ongoing research into whether primordial magnetic fields permeate voids or whether fields leak out from galaxies over time. Even extremely weak fields can influence charged particles and the propagation of cosmic rays. Speaking of cosmic rays, high-energy particles pass through voids largely unimpeded. Dense regions can scatter and absorb them. Voids act more like transparent corridors. This affects how cosmic rays propagate across the universe and how we interpret their origins. Then there are the galaxies themselves. Voids are not completely devoid of galaxies. They just contain far fewer of them, and the ones that exist there are different. Void galaxies tend to be small, faint, and rich in gas. They are often irregular in shape and show signs of slow, steady star formation rather than violent bursts. Because they have few neighbors, they rarely experience mergers or strong tidal interactions. This isolation matters. In dense environments, galaxy evolution is heavily influenced by surroundings. Gas can be stripped away, star formation can be quenched. Morphologies can be transformed. In voids, galaxies are left mostly to their own devices. As a result, void galaxies can preserve conditions that were common earlier in cosmic history. Some have low metallicity, meaning they contain fewer heavy elements produced by previous generations of stars. This suggests a slower evolutionary pace. However, even within voids, galaxies are not distributed randomly. They often trace faint internal filaments of dark matter. These filaments are much less massive than the main cosmic web, but they still guide where the few galaxies form. This means that voids have structure within structure. The emptiest regions are typically near the centers of voids. Toward the edges, densities increase and small filaments appear. The transition from void interior to filament is gradual, not abrupt. Another important point is that voids are dynamically active. Matter is constantly flowing. Dark matter and gas move outward from the center toward the boundaries. Galaxies near the edges feel this flow and can have peculiar velocities directed away from the void interior. From a gravitational perspective, voids behave almost like negative mass regions, not because they repel matter, but because they lack the mass that would otherwise pull things inward. Surrounding regions dominate gravitationally, drawing matter out. This dynamic behavior makes voids sensitive to cosmological parameters. The rate at which they expand depends on how fast the universe as a whole is expanding and on how gravity behaves on large scales. This sensitivity is one reason voids are used to test models of dark energy and modified gravity. Changes in cosmic acceleration affect voids more cleanly than they affect dense regions, where complex astrophysics can mask subtle effects. There's also a geometric aspect to what's inside voids. Space itself expands everywhere, but inside voids the expansion is slightly faster. Over time, this stretches any internal structure, making void interiors smoother and emptier. Small-scale irregularities get washed out. This smoothing effect is another reason voids are relatively simple environments. They preserve large-scale information while erasing small-scale noise. It's also worth noting what voids don't contain. They lack large galaxy clusters. They lack hot, X-ray emitting gas. They lack strong gravitational lensing effects. They lack intense radiation fields from active galactic nuclei. All of these absences contribute to their observational invisibility. If you were floating inside the center of a large void, the universe would look profoundly different. The sky would contain far fewer galaxies. The nearest bright structures would be unimaginably distant. The sense of cosmic isolation would be extreme, and yet, from a physical standpoint, you would still be embedded in a fully functioning universe. Gravity would still act. Time would still flow normally. The cosmic microwave background would still surround you. This duality, extreme emptiness without physical nothingness, is what makes voids such powerful laboratories. They isolate the effects of gravity and expansion from the clutter of astrophysical processes. Understanding what's inside the largest voids also helps explain how they form and evolve. Their contents, or lack thereof, are not accidental. They are the outcome of a long history of matter flowing away, structure failing to form, and expansion winning out over gravity. That history doesn't stop at matter and radiation. It extends to the galaxies that manage to survive there and how their lives differ from those in crowded regions. To see how emptiness shapes evolution on smaller scales, we need to zoom in on those rare inhabitants of the void and follow their slow, isolated lives over cosmic time. A galaxy born inside a cosmic void grows up under very different conditions than one in a crowded filament or cluster. The laws of physics are the same, but the environment changes everything about how those laws play out over billions of years. The first difference is timing. In dense regions, small dark matter halos form early. They merge, accrete gas, and trigger star formation quickly. In voids, collapse is delayed. The dark matter halos that do form are typically smaller and assemble later. That means galaxies in voids often begin their lives later than their counterparts in denser environments. This delay has long-term consequences. When a galaxy forms later, it does so in a universe that is already older, cooler, and more expanded. Gas densities are lower. The background radiation field is weaker. These conditions make it harder for gas to cool and collapse efficiently. As a result, void galaxies tend to be low-mass systems. They often have shallow gravitational potentials, which makes them vulnerable in some ways, but also protects them in others. Because they're isolated, they avoid disruptive interactions. But because their gravity is weak, they struggle to hold onto gas once energetic events occur. Most void galaxies are rich in neutral hydrogen. They have large reservoirs of cold gas relative to their stellar mass. This gas fuels slow, steady star formation rather than rapid bursts. Star formation rates are typically low, but they can persist for a very long time. This slow pace is a defining feature. In dense environments, star formation is often triggered by interactions, galaxy mergers, close flybys, tidal forces. These events compress gas and ignite bursts of star formation. In voids, such triggers are rare or non-existent. Star formation proceeds quietly, governed by internal processes rather than external shocks. This leads to different stellar populations. Void galaxies often contain a higher fraction of young stars relative to their mass, not because they form stars rapidly, but because they never experienced a dramatic shutdown. Star formation just never got interrupted. Another striking difference is morphology. Void galaxies are more likely to be irregular or disk-like rather than elliptical. Elliptical galaxies typically form through mergers, which are rare in voids. Without frequent collisions, galaxies retain their original shapes for longer. Spiral structure can still form, but it's often less pronounced. Bars and warps may develop through internal instabilities rather than interactions. The overall appearance is simpler, less disturbed. Metallicity tells another part of the story. Metals, elements heavier than helium, are produced in stars and spread through galaxies by supernova and stellar winds. In void galaxies, metallicity is often lower than in similar mass galaxies, in denser regions. This reflects fewer generations of star formation and less recycling of enriched material. Some void galaxies have metallicities comparable to those expected in the early universe. This makes them valuable targets for studying star formation under primitive conditions, even at relatively late cosmic times. Isolation also affects feedback. When massive stars explode as supernovae, they inject energy into their surroundings. In a dense environment, surrounding gas and neighboring galaxies can help confine this energy. In a void galaxy, the surrounding medium is thin. Energy escapes more easily. This can have a dual effect. On one hand, it can blow gas out of the galaxy, suppressing future star formation. On the other, the lack of external pressure means that outflows can vent without disrupting the remaining gas too violently. The balance depends on galaxy mass and star formation history. Another important difference is the absence of environmental quenching. In clusters, galaxies can lose gas through processes like ram pressure stripping as they move through the hot intracluster gas. Tidal forces can strip stars and dark matter. None of this happens in voids. Once a galaxy forms, it keeps its gas unless it loses it through internal processes. This makes void galaxies cleaner laboratories for studying internal galaxy evolution. Many of the confounding variables present in dense regions simply aren't there. Despite their isolation, void galaxies are not entirely alone. They can have companions, but these companions are usually small and far apart. Interactions, when they do occur, are slow and gentle compared to high-speed cluster encounters. These rare interactions can still matter. Even a minor merger can reshape a small galaxy, trigger a burst of star formation, or fuel a central black hole. But such events are spaced out over long timescales. Speaking of black holes, void galaxies tend to host smaller central black holes, if they host them at all. The growth of supermassive black holes is closely tied to mergers and gas inflows, both of which are limited in void environments. Active galactic nuclei are therefore less common in voids, and when present, they are typically weaker. This further reduces feedback that could shut down star formation. Another consequence of void life is kinematics. Galaxies inside voids often participate in coherent outflows away from the void center. Their peculiar velocities are influenced by the overall expansion of the void. This can subtly affect how their redshifts are interpreted and how their motions are modeled. Over cosmic time, many void galaxies drift toward the edges of voids, joining filaments. The void interior becomes increasingly empty. This means the galaxies we observe deep inside voids today are survivors, systems that formed and remained isolated long enough to still be there. There's also evidence that void galaxies may be more dark matter dominated than similar galaxies elsewhere. Their shallow potentials and low stellar masses mean dark matter contributes a larger fraction of their total mass. This makes them useful for testing models of dark matter behavior on small scales. However, it's important not to over-romanticize void galaxies as pristine relics. They still evolve. They still form stars. They still interact with their internal environment. They're just doing so in slow motion. In many ways, void galaxies are examples of what galaxy evolution looks like when you remove most external influences. That makes them valuable reference points. By comparing galaxies in voids with those in filaments and clusters, astronomers can isolate the role of environment in shaping galaxies. Differences in star formation, morphology, metallicity, and kinematics can be traced back to density and interaction history. This comparative approach has sharpened our understanding of galaxy formation as a whole. It's shown that many features we once thought were intrinsic are actually environmental. And it reinforces a broader lesson. Emptiness shapes structure just as much as density does. The behavior of galaxies inside voids is a direct consequence of how voids form in the first place. To understand that formation process more deeply, we need to look at the underlying force driving it all, gravity, and how it behaves when there's almost nothing to work with. At first glance, it seems counterintuitive that gravity, the force that pulls matter together, could be responsible for creating vast regions of emptiness. But gravity doesn't just build structures, it redistributes matter. And when it does that unevenly, emptiness is a natural outcome. The key is that gravity amplifies differences. In the early universe, matter was distributed almost uniformly, but not perfectly. Tiny fluctuations in density existed everywhere. Some regions were slightly denser than average, others were slightly less dense. Gravity acted on both, but not symmetrically. In denser regions, gravity pulled matter inward. As matter accumulated, gravity strengthened, pulling in even more material. This positive feedback led to the formation of filaments, clusters, and galaxies. In underdense regions, the opposite happened. There was less mass to begin with, so gravitational attraction was weaker. Surrounding denser regions exerted a stronger pull, drawing matter out. Over time, this drained the underdense region even further, So gravity didn't push matter out of voids. It simply pulled matter more strongly toward nearby overdensities. This distinction matters. There is no repulsive force acting inside voids. Everything obeys the same gravitational laws. The emptiness emerges from imbalance, not reversal. Another crucial factor is geometry. Gravity acts in 3 dimensions, but collapse happens fastest along the shortest axis of a region. In overdense regions, this leads to anisotropic collapse. Matter first collapses into sheets, then filaments, then nodes. In underdense regions, expansion proceeds preferentially along certain directions, stretching the region into elongated shapes. This anisotropic behavior is why voids are rarely perfect spheres. Their shapes reflect the surrounding density field and the directions in which matter can most easily flow outward. As matter leaves a void, the gravitational potential inside becomes shallower. This reduces the ability of the void to retain matter in the future. The process reinforces itself. Once a region starts losing matter, it tends to keep losing it. This is why voids are long-lived. They don't fill back in. It might seem like over time, matter from surrounding regions would drift back into voids and smooth everything out. But the opposite happens. The large-scale expansion of the universe stretches space everywhere. In dense regions, gravity can overcome that expansion locally. In voids, gravity is too weak to counteract it effectively. The result is that voids expand faster than average. Their boundaries move outward relative to the cosmic expansion. Matter inside is diluted more rapidly than elsewhere. This faster expansion is not dramatic in absolute terms, but over billions of years, it becomes significant. A region that was only mildly underdense early on can become extremely empty by the present day. This behavior can be described quantitatively. In cosmological models, voids follow a specific expansion history. Their internal expansion rate exceeds the global Hubble expansion. This leads to a characteristic velocity pattern. Matter flows outward from the center toward the edges. These flows can be measured statistically by observing galaxy motions around voids. The results match theoretical predictions, providing strong evidence that gravity and expansion alone can explain void dynamics. Another important aspect is scale coupling. Small-scale fluctuations ride on top of large-scale ones. A region that is underdense on large scales will suppress the growth of smaller structures within it. Even if a small overdensity exists inside a void, its growth is slowed by the overall expansion and low background density. This suppression explains why voids contain fewer small galaxies than naive models might predict. It's not just that matter left the region, it's that structure formation was hindered from the start. Gravity also shapes void boundaries. As matter flows out, it piles up along the edges, forming walls and filaments. These structures are not separate from the void, they are its consequence. The sharper the contrast between void and surroundings, the more pronounced these boundaries become. In extreme cases, this leads to a nearly shell-like appearance where galaxies trace the perimeter of a void, emphasizing the emptiness inside. This shell formation further stabilizes the void. The mass accumulated at the edges deepens the gravitational wells there, making it even harder for matter to drift back inward. There's also an interesting asymmetry between overdensities and underdensities. Overdense regions eventually reach a point where gravity halts expansion and leads to collapse. Underdense regions never collapse. They expand forever. This means voids continue to grow in relative importance as the universe ages. As time goes on, more matter ends up locked into dense structures, while more volume becomes dominated by voids. In the far future, this contrast will be even stronger than it is today. This has implications for the large-scale fate of the universe. If dark energy continues to drive accelerated expansion, voids will expand even faster relative to dense regions. Filaments and clusters will become increasingly isolated islands of matter, separated by vast expanding emptiness. Gravity, paradoxically, will be the force that ensures emptiness dominates the cosmos by volume. Another subtle role of gravity involves tidal forces. Voids are influenced by the gravitational pull of surrounding structures. These tidal forces can stretch voids, align them with filaments, and influence their shapes. Voids are not independent entities. They respond to the broader mass distribution. This interaction means that studying void shapes and orientations can reveal information about the large-scale gravitational field. Voids act as tracers of tidal environments, complementing studies of dense regions. The interplay between gravity and expansion also explains why voids are sensitive to changes in gravitational physics. If gravity behaved differently on large scales, or if dark energy evolved differently over time, void expansion rates would change. This would alter void sizes, shapes, and internal dynamics. This sensitivity makes voids powerful probes. They magnify subtle effects that are hard to detect in dense regions where nonlinear processes dominate. So while gravity is usually associated with building things, stars, galaxies, clusters, it is just as responsible for tearing things apart, at least in a relative sense. By pulling matter unevenly, it sculpts both structure and emptiness. The largest voids are simply the most extreme examples of this process. They are regions where gravity, acting over billions of years, systematically failed to assemble matter into anything substantial. But gravity is not acting alone. The universe is expanding, and that expansion is not constant. Something else is influencing how quickly space stretches, especially in low-density regions. To understand why voids behave the way they do today, and why they may be even more important in the future, we have to bring dark energy into the picture. If gravity explains why voids form, cosmic expansion explains why they keep getting bigger, and why emptiness becomes more dominant as the universe ages. To understand the largest empty spaces we see today, you have to follow their history across billions of years, from a nearly uniform early universe to the sharply contrasted one we live in now. Early on, voids barely existed. In the first few 100,000 years after the Big Bang, the universe was hot, dense, and smooth. Matter and radiation were tightly coupled, and density differences were tiny. When the universe cooled enough for atoms to form and light to travel freely, those density differences were still extremely small. Voids, in any meaningful sense, were barely distinguishable from their surroundings. At that stage, everything was expanding together. There was no clear separation between regions that would later become dense and those that would become empty. The separation began slowly. As the universe expanded and cooled, matter began responding more strongly to gravity. Overdense regions started pulling matter inward. Underdense regions, by contrast, began losing matter to their surroundings. This was the first step in void formation, but the contrast was weak. Early voids were shallow and poorly defined. At this point, expansion dominated everything. Gravity was only just beginning to leave its imprint. As time went on, the balance shifted. In overdense regions, gravity gradually overcame expansion on small scales. Structures began to decouple from the Hubble flow. Matter collapsed into filaments and halos. Star formation began. These regions slowed their local expansion and, in some cases, stopped expanding altogether. In underdense regions, the opposite happened. There was never enough mass to counteract expansion. As matter drained away, gravity became even less effective. Expansion continued essentially unhindered. This divergence is the key to void growth. A void does not just passively expand with the universe, it expands faster than average. The local expansion rate inside a void is higher than the global expansion rate because there is less mass to slow it down. Over billions of years, this small difference compounds. Imagine two regions starting at roughly the same size. One contains slightly less matter than average. At first, the difference is negligible. But as the universe expands, the underdense region stretches a little more each second than the average region. After 1 billion years, that extra stretching adds up. After 10 billion years, it becomes dramatic. This is why voids grow in relative size, even if their absolute growth seems modest. Another important aspect of void evolution is merging. Voids don't exist in isolation. Early in the universe, many small underdense regions formed. As expansion continued and matter flowed outward, these small voids expanded and began to overlap. When the boundary between two voids became sufficiently thin, the voids effectively merged into a larger one. This process is hierarchical, just like structure formation on the dense side of the cosmic web. Small voids form first. Larger voids emerge later through merging and expansion. The largest voids we see today are the end products of this long process. This merging is not symmetric. When two voids merge, the region between them doesn't collapse. Instead, it becomes even more underdense as matter continues to flow away. The merged void tends to be larger and more irregular in shape than either progenitor. This explains why the largest voids often have complex non-spherical geometries. They are not single, pristine underdensities. They are composite structures formed from multiple voids that grew together. As voids expand, their interiors evolve. Early void interiors may contain small, dark matter halos and faint galaxies. Over time, many of these drift outward toward the edges. The central regions become progressively emptier and smoother. This evacuation process is slow but relentless. The density contrast between the center and the edges increases with time. This is why voids are often described as aging. Older voids are larger, emptier, and smoother. Younger voids are smaller, less empty, and more structured. The age of a void is not measured in years, but in how far it has progressed along this evolutionary path. Another key factor in void expansion is the transition from matter-dominated to dark energy-dominated expansion. For the first several billion years of cosmic history, matter dominated the universe's dynamics. Expansion was slowing due to gravity, even in voids. Underdense regions still expanded faster than average, but the overall expansion rate was decreasing. As dark energy became dominant, this changed. When dark energy began to drive accelerated expansion, low-density regions responded most strongly. Dense regions remained bound or slowed by gravity. Voids, already weakly bound, felt the full effect of accelerated expansion. This further enhanced the growth of voids relative to dense regions. In practical terms, this means that voids have grown more rapidly in the last several billion years than they did earlier in cosmic history. The largest voids today owe much of their size to this late-time acceleration. This also means void evolution is sensitive to the nature of dark energy. Different models of dark energy predict different expansion histories for voids. Measuring how void sizes change with redshift, how they look at different points in cosmic time, provides a way to test those models. Another aspect of void expansion involves shape evolution. As voids expand, they tend to become rounder over time, but never perfectly spherical. Early voids are strongly shaped by surrounding density fields and tidal forces. As expansion smooths the interior, small-scale irregularities are erased. However, large-scale tidal forces remain. These forces stretch voids along preferred directions, often aligning them with nearby filaments. The result is a balance between smoothing and stretching. This is why voids often appear elongated or flattened rather than spherical. The rate at which voids expand is not uniform across their volume. The center expands fastest. The edges expand more slowly, influenced by the gravity of surrounding structures. This creates a gradient in expansion rate from the center outward. This gradient affects galaxy motions. Galaxies near the center of a void tend to move outward more rapidly relative to the Hubble flow. Galaxies near the edges experience more complex dynamics, influenced by both void expansion and attraction to filaments. These velocity patterns are measurable. By studying redshift space distortions around voids, astronomers can infer how fast voids are expanding and compare that to theoretical predictions. The agreement between observations and simulations here is one of the quiet successes of modern cosmology. Void expansion also affects the fate of matter within them. Gas inside voids becomes increasingly diffuse over time. Its temperature and ionization state evolve as it expands. Star formation becomes less likely as densities drop further. Any galaxies that remain in the interior tend to be small and gas-rich, evolving slowly. Eventually, many void interiors may become nearly devoid of bound structures altogether. Looking far into the future, this trend continues. As expansion accelerates, voids will dominate an even larger fraction of the universe's volume. Filaments and clusters will remain bound internally, but they will move farther apart. The contrast between dense islands of matter and vast empty regions will sharpen. In that distant future, the universe will look more like a collection of isolated structures floating in enormous voids than the interconnected web we see today. This future trajectory underscores something important. Voids are not static background features. They are dynamic, evolving entities that play an active role in shaping cosmic history. Their growth influences how matter is distributed, how galaxies move, and how light travels across the universe. Ignoring voids would give an incomplete picture of cosmic evolution. The expansion of voids also feeds back into structure formation. As voids grow, they push matter into filaments, enhancing those structures. This makes the cosmic web more pronounced over time. In this sense, voids and filaments co-evolve. One cannot exist without the other. Understanding this coevolution is crucial for interpreting large-scale surveys. When astronomers observe the universe at different redshifts, they are seeing voids at different stages of their lives. Comparing those stages helps reconstruct the full growth history of cosmic structure. This is why voids are increasingly used as time machines. They preserve information about expansion and gravity that dense regions tend to erase through complex nonlinear processes. So when we talk about the largest empty spaces in the universe, we're not talking about ancient scars left behind early on and frozen in place. We're talking about features that are still growing, still changing, still responding to the balance between gravity and expansion. And that balance depends on something we've only mentioned indirectly so far. Expansion is not just happening, it's accelerating. To understand why voids are such sensitive probes of that acceleration, and why they may help us understand one of the biggest open questions in cosmology, we need to look directly at the role of dark energy in shaping emptiness. Dark energy doesn't announce itself with explosions or radiation. It doesn't clump. It doesn't form structures. Its influence only becomes obvious when you look at how space itself behaves, and nowhere is that behavior clearer than inside cosmic voids. To see why, it helps to be precise about what dark energy actually does. Dark energy affects the expansion of space, not the motion of objects through space in the usual sense. It changes how fast distances between unbound regions grow over time. Dense regions can resist this because gravity holds them together. Low-density regions cannot. Voids are the lowest density environments in the universe. That makes them the cleanest places to observe the effects of dark energy. Before dark energy became important, expansion was slowing everywhere due to gravity. Matter dominated the dynamics. Even voids, though they expanded faster than average, were still part of a universe whose expansion rate was decelerating. That changed when dark energy took over. Once dark energy became the dominant component of the universe's energy budget, expansion stopped slowing down and began to accelerate. This didn't affect all regions equally. Dense structures barely noticed. Voids noticed immediately. Inside a void, there is very little mass to counteract the effect of dark energy. Gravity is weak. That means the acceleration of expansion inside voids is closer to the pure effect of dark energy than anywhere else. This makes voids behave almost like test chambers for cosmic acceleration. One way to see this is through relative expansion rates. In a universe without dark energy, voids would still expand faster than average, but the difference would be limited. With dark energy, that difference grows over time. The expansion inside voids accelerates more strongly than the expansion near dense regions. This causes voids to grow not just larger, but dynamically distinct. Their internal velocity fields change. Matter flows outward more efficiently. Bound structures inside voids become rarer. The contrast between void interiors and their edges sharpens. This is not just a qualitative idea. It shows up in simulations and observations. When cosmologists run simulations with dark energy included, voids at late times are larger, emptier, and more spherical on average than in simulations without it. The differences are subtle but measurable. That sensitivity is crucial. Most traditional cosmological probes focus on dense regions, galaxy clustering, cluster counts, gravitational lensing. These are powerful, but they are complicated. Gas physics, star formation, feedback from black holes. All of these muddy the signal. Voids avoid much of that complexity. Inside voids there is little gas cooling, little star formation, and minimal nonlinear collapse. The physics is dominated by gravity and expansion. That makes voids cleaner probes of cosmological parameters. One specific effect is the void expansion rate. By measuring how galaxies move around voids, astronomers can infer how fast voids are expanding relative to the cosmic average. This expansion rate depends directly on the properties of dark energy. If dark energy was stronger, voids would expand faster. If it evolved over time, void growth histories would change accordingly. This opens the door to using voids as cosmic chronometers. By observing voids at different redshifts, different stages of cosmic history, astronomers can track how their sizes, shapes, and internal dynamics evolve. Comparing this evolution to theoretical predictions allows constraints on dark energy models. Another important observable is void shape. Dark energy influences how voids respond to tidal forces. In a universe dominated by dark energy, voids tend to become more spherical over time, because accelerated expansion smooths out internal anisotropies. In contrast, in models with modified gravity or different dark energy behavior, void shapes can evolve differently. They may remain more elongated or show stronger alignment with surrounding structures. Statistical studies of void ellipticity and orientation can therefore test fundamental physics. There's also the integrated effect of voids on light. As photons pass through a void, they experience a slightly different gravitational environment than they would in a uniform universe. In an accelerating universe, this leads to subtle changes in photon energy as they enter and exit voids. This effect is tiny, but over many voids it becomes detectable as correlations between large-scale structure and background radiation. These signals depend on how the gravitational potential of voids evolves over time, which in turn depends on dark energy. In practical terms, voids leave faint imprints on the cosmic microwave background and on galaxy redshifts. Measuring these imprints provides another way to probe cosmic acceleration. What makes this especially powerful is that void-based measurements are complementary to traditional methods. They respond differently to systematic errors. They depend on different aspects of the physics. When multiple independent probes point to the same conclusion, confidence increases. Voids also help test alternatives to dark energy. Some theories attempt to explain cosmic acceleration by modifying gravity itself rather than invoking dark energy. These theories often predict different behavior in low-density environments. In many modified gravity models, deviations from general relativity are suppressed in dense regions but become apparent in voids. This makes voids prime locations to look for such effects. For example, some models predict enhanced gravitational forces in underdense regions, which would change void expansion rates and galaxy motions. Others predict different relationships between void size and depth. By carefully measuring void properties, astronomers can rule out or constrain these alternatives. So far, observations of voids are broadly consistent with a universe dominated by dark energy behaving like a cosmological constant. But the uncertainties are still large, and void studies are improving rapidly as surveys grow. There's another, more conceptual way dark energy reshapes our understanding of voids. In a universe with accelerated expansion, the future is increasingly dominated by emptiness. Voids are not just features of the present. They are previews of the universe's long-term fate. As time goes on, bound structures remain bound, but the space between them expands exponentially. Voids grow until they encompass almost all volume. Filaments thin out. Clusters become isolated islands. From this perspective, voids are not anomalies. They are the default outcome of cosmic evolution under dark energy. That reframes how we think about structure. Rather than seeing galaxies and clusters as filling space, it's more accurate to see them as rare exceptions embedded in a vast, expanding background of emptiness. Voids are not the absence of structure. They are the dominant structure by volume. Dark energy ensures that this dominance increases with time. This also means that studying voids is not just about understanding the present universe. It's about understanding where the universe is headed. The largest voids we see today are still relatively young in cosmic terms. In tens of billions of years, they will be far larger, far emptier, and far more dominant. If observers existed in that far future, their view of the universe would be radically different. They would see only a few nearby galaxies with vast darkness in between. The cosmic web would be effectively invisible beyond local scales. In that sense, voids are windows into both the deep past and the distant future. They preserve information about initial conditions because they evolve simply, and they foreshadow the universe's eventual state because they respond most strongly to acceleration. All of this makes voids unusually powerful tools for cosmology, but only if we can identify and measure them accurately. That turns out to be harder than it sounds. Voids are defined by what's missing, not by what's present. Their boundaries are fuzzy, their shapes are irregular, their depths vary. How you define a void affects what you measure. This is why void studies rely heavily on large, uniform galaxy surveys and careful statistical methods. As data improves, so does our ability to use voids as precision instruments. And that brings us to a practical question. When astronomers claim to have found the largest void, what exactly do they mean? How do they detect something defined by emptiness? And how confident can we be that such enormous voids are real, three-dimensional structures rather than artifacts of limited data? To answer that, we need to step away from theory and look at how voids are actually observed and mapped in the real universe. Finding something by its absence is always harder than finding something that shines. That's the fundamental challenge with cosmic voids. They don't emit light, they don't block it, and they don't announce clear edges. Astronomers have to infer their existence indirectly, using the distribution and motion of galaxies as traces of the underlying matter field. The basic idea is simple. Where there are few galaxies, there is likely a void. But turning that idea into a rigorous measurement is anything but simple. The first step is mapping galaxies in 3 dimensions. Modern galaxy surveys don't just record positions on the sky. They measure redshifts, which give distances through cosmic expansion. With enough galaxies and enough sky coverage, astronomers can reconstruct a 3-dimensional map of where matter is concentrated and where it's sparse. Early surveys were too small and too shallow to do this reliably. They revealed hints of voids, but couldn't capture their full extent. As surveys grew in size and depth, the picture sharpened. Once you have a galaxy map, the next step is defining what counts as a void. There is no single universal definition. Different methods exist, each with trade-offs. Some algorithms look for spherical regions with galaxy densities below a certain threshold. These methods are simple and intuitive, but they impose artificial shapes. Real voids are rarely spherical. Other methods identify local density minima and grow voids outward until a boundary condition is met. These capture irregular shapes better, but can be sensitive to noise and survey geometry. More sophisticated approaches use the topology of the density field. They treat the galaxy distribution as a continuous field and identify basins, regions that drain toward local minima. This approach aligns well with theoretical expectations of how voids form and merge. Each method produces slightly different catalogues of voids. This is why different studies sometimes quote different sizes for the largest voids. Another complication is sampling. Galaxies are not perfect traces of matter. They form preferentially in dense regions. This means void interiors are undersampled by design. A truly empty region and a region with a few faint galaxies can look similar in a sparse survey. To address this, astronomers use statistical corrections and compare observations with simulations that include realistic galaxy formation models. This helps translate galaxy counts into underlying matter densities. Survey boundaries also matter. Voids near the edge of a survey can appear artificially large or distorted because data is missing beyond the boundary. Careful masking and selection are needed to avoid false detections. Redshift distortions add another layer of complexity. Galaxy redshifts include not just cosmic expansion, but also peculiar velocities, motions caused by gravity. In voids, these velocities tend to be outward, which can stretch voids along the line of sight in redshift space. This can make voids appear larger or more elongated than they are in real space. Correcting for this requires models of galaxy motions and careful statistical analysis. Despite these challenges, large surveys have converged on a consistent picture. Voids are real, 3-dimensional structures. Their size distribution, shapes, and abundance match predictions from cosmological simulations reasonably well. The largest voids identified are not single clean bubbles. They are extended regions of underdensity composed of multiple connected subvoids. Their effective sizes depend on how you measure them. This is why astronomers sometimes distinguish between voids and supervoids. A void is typically defined as a single basin in the density field. A supervoid is a larger region where several voids overlap or align, creating an extended underdensity. Supervoids can span hundreds of millions of light-years and are often associated with large-scale anomalies in galaxy distributions or background radiation. One of the most discussed examples is the Eridanus supervoid, identified in the direction of a cold region in the cosmic microwave background. This structure appears as a broad underdensity extending over a significant range of distances. Interpreting such structures requires caution. A supervoid may not be uniformly empty. It may contain smaller voids, filaments, and galaxies. What matters is the average density over a large volume, not the absence of all structure. Another observational tool is gravitational lensing. Even though voids contain little matter, they still affect light. Their underdensity causes a slight divergence of light rays passing through them. By statistically measuring distortions in background galaxies, astronomers can infer the mass deficit associated with voids. This method is powerful because it probes matter directly, not just galaxies. It provides an independent check on void properties inferred from galaxy counts. Lensing measurements confirm that voids correspond to genuine deficits in mass, not just missing galaxies. Another technique involves galaxy velocities. As mentioned earlier, galaxies tend to move outward from void centers. By measuring these motions statistically, astronomers can infer void expansion rates and depths. These measurements are consistent with the gravitational picture of void evolution. Combining these methods, galaxy counts, topology, lensing, and velocities, gives a more complete picture. It also highlights an important limitation. No void is perfectly defined. Boundaries are fuzzy. Depth varies with location. Size depends on threshold. This is not a failure of observation. It reflects the physical reality of how underdensities form. This fuzziness is why claims about the largest void are always contextual. They depend on definition, survey, and method. That said, there is a consensus that voids with effective diameters of several 100 million light-years exist and are not rare at the largest scales probed by modern surveys. There is also consensus that much larger, truly coherent voids, on the scale of 1 billion light-years or more, would be difficult to reconcile with standard cosmology unless they were composite structures rather than single entities. This distinction becomes important when voids are invoked to explain other phenomena. Occasionally, large underdensities are proposed as explanations for anomalies in cosmic observations. In those cases, the question is not just whether an underdensity exists, but whether it has the right size, shape, and depth to produce the observed effect. This is where void studies intersect with some of the more controversial corners of cosmology. Claims about extremely large voids sometimes arise in attempts to explain features like unusual temperature patterns in the cosmic microwave background, or apparent deviations in cosmic expansion measurements. Some of these ideas are intriguing. Others do not survive careful scrutiny. Understanding how voids are detected, defined, and measured is essential for separating plausible explanations from speculative ones. It also underscores a broader point. Emptiness is harder to measure than matter. Despite that, the picture of the universe dominated by vast voids is one of the most robust results of modern cosmology. We now know how to find them, how to measure them, and how to interpret them within a solid theoretical framework. But there's one more question that tends to capture attention, both inside and outside astronomy. What would it actually be like to be inside the largest empty space in the universe? Not in an abstract sense, but observationally. What would you see? What would the sky look like? How different would your cosmic environment really feel? To answer that, we have to shift perspective, from mapping voids from the outside to imagining a view from deep within. Imagine removing nearly all nearby reference points from the sky. No bright galaxy clusters. No thick filaments crossing your field of view. Just a sparse scattering of faint galaxies, most of them far away and barely resolved. That's what the universe would look like from deep inside a large cosmic void. The first thing you would notice is scale. Distances would feel extreme. The nearest major galaxy cluster could be hundreds of millions of light-years away. Even ordinary galaxies would be much more widely spaced than anything we're used to. The familiar sense of a crowded cosmic neighborhood would be gone. The sky would not be dark exactly, but it would be thin. There would still be galaxies in every direction, but they would be fewer and dimmer. The Milky Way itself, seen from such a location, would likely be one of the brightest objects in the sky, simply because there would be so little competition nearby. Large, bright spirals would be rare. Elliptical galaxies and clusters would be almost absent. Most visible galaxies would be small, faint, and isolated. The distribution would also feel uneven. Rather than a roughly uniform background of galaxies, you would notice subtle patterns. Faint alignments hinting at distant filaments. Slight concentrations in particular directions where the void walls lie far away. The sky would be dominated by emptiness, but not randomness. Another striking difference would be the lack of strong gravitational landmarks. In our own cosmic environment, massive structures subtly influence everything. They bend light, affect galaxy motions, and leave imprints on the background radiation. Inside a void, these effects would be minimal. Gravitational lensing would be weak. There would be few dramatic arcs or distortions. The paths of light rays would be closer to straight lines over vast distances. This would slightly change how the universe appears on large scales. The absence of strong lensing would make distant objects appear more uniformly distributed and less distorted. The cosmic microwave background would still be there. From inside a void, the CMB would look almost exactly as it does from anywhere else. Its temperature would be the same to high precision. Its small-scale fluctuations would be unchanged. However, there could be subtle differences on very large angular scales due to the local gravitational environment. These differences would be tiny, far below what a human eye could detect, but measurable with precise instruments. The biggest change would not be visual, it would be dynamical. Galaxies inside the void would be moving away from you slightly faster than the cosmic average. This is not because of any local explosion, but because the void is expanding faster than denser regions. If you measured redshifts carefully, you would find that nearby galaxies recede a bit faster than expected from the global Hubble expansion. This local super-Hubble flow is a characteristic signature of voids. This would affect distance measurements. Standard candles and rulers would behave subtly differently inside a void. Without accounting for the local underdensity, you could misestimate cosmic expansion rates. This is one reason why local measurements of expansion need to consider environmental effects. Time itself would feel the same. Clocks would tick normally. Physical processes would proceed at the same rates. There is no time dilation effect associated with living in a void. Gravity would still operate normally on local scales. Stars would orbit normally. Planets would behave as usual. There is no sense in which a void is a strange or hostile environment locally. The difference is entirely about large-scale context. The intergalactic medium inside a void would be extremely thin. Gas densities would be so low that interactions between particles would be rare. Any radiation traveling through would encounter little resistance. Cosmic rays would travel long distances without scattering. Intergalactic magnetic fields would be weak and disordered. From an observational standpoint, this could be an advantage. If you wanted to study distant galaxies or background radiation with minimal interference, a void would be an excellent place to do it. There would be less foreground contamination, less lensing, and fewer confusing structures along the line of sight. On the other hand, the lack of nearby objects would limit certain kinds of astronomy. Detailed studies of galaxy clusters, gravitational interactions, and dense environments would require looking very far away. Another subtle effect involves reference frames. Because matter is sparse, defining a rest frame inside a void is less straightforward. The local velocity field is dominated by expansion rather than by the motion of nearby mass concentrations. This could complicate precise measurements of cosmic flows. Despite these differences, the universe inside a void is not exotic in a science fiction sense. It is quiet, sparse, and uneventful. The most profound change would be psychological rather than physical. If intelligent observers evolved inside a large void, their picture of the universe might be very different. With so few nearby galaxies, it might take longer to realize the true scale of cosmic structure. The cosmic web would be harder to infer from local observations. Paradoxically, such observers might conclude that the universe is more uniform than it really is, simply because they lack access to dense regions nearby. This idea has been explored seriously in cosmology. It highlights how location matters when interpreting observations. Our own position near filaments and clusters gives us a biased view of what's typical. The typical environment in the universe is emptier than where we live. Living inside a void would make that fact obvious. There's also an important implication for cosmological measurements. If we live deep inside a very large void, local measurements of expansion could differ from the global average. This has led to occasional proposals that apparent discrepancies in expansion measurements could be explained by our location inside an underdensity. Most of these proposals fail when confronted with detailed data, but they illustrate how voids can influence interpretation. Ultimately, being inside the largest empty space in the universe would not feel strange on human scales, but on cosmic scales, it would profoundly alter what you see, what you measure, and what conclusions you draw about the universe. This shift in perspective is one reason voids matter beyond their physical properties. They remind us that cosmic observations are always made from somewhere, and that somewhere is not necessarily typical. Understanding voids helps correct for that bias, and it brings us back to the broader question of meaning. Voids take up most of the universe's volume. They shape how matter is distributed. They influence expansion, light propagation, and galaxy evolution. Yet they are defined by what they lack. So are voids just empty byproducts of structure formation, or do they play a deeper role in shaping the universe? To answer that, We need to step back one last time and look at voids not as places, but as cosmic actors, features that actively influence how the universe behaves on the larger scales. On the larger scales, the universe behaves less like a collection of objects and more like a pattern. And in that pattern, voids are not passive gaps between important things. They are active components that help determine how everything else is arranged. The easiest way to see this is to flip the usual perspective. Instead of asking how galaxies shape voids, ask how voids shape galaxies. Every void pushes matter outward, not with a force but through imbalance. As voids expand faster than average, they drive matter toward their boundaries. This process feeds filaments, thickens walls, and sharpens clusters. Without voids, the cosmic web would not exist in its familiar form. Filaments are not independent structures that happen to connect galaxies. They are the compressed leftovers of matter, displaced by growing voids. Clusters form at the intersections where multiple voids meet and matter has nowhere else to go. In this sense, voids are sculptors. Dense structures are the material they leave behind. This also means that voids influence where galaxies form in the first place. Regions that will become voids suppress structure formation early. Galaxies form later, if at all. Regions destined to lie near void boundaries experience enhanced matter inflow and earlier collapse. This creates a built-in environmental bias that persists for billions of years. So when we observe differences between galaxies in clusters, filaments, and voids, we're seeing the long-term consequences of where those galaxies sit relative to expanding emptiness. Voids also influence how matter moves on large scales. Cosmic flows are not random. They are guided by the geometry of voids and the locations of dense regions around them. Matter flows away from void centers and toward filaments and nodes. These flows set up velocity patterns that extend across hundreds of millions of light years. These motions affect galaxy redshifts, clustering statistics, and even how we interpret cosmic distances. Ignoring void-driven flows would lead to systematic errors in large-scale measurements. Voids also affect how information travels through the universe. Light passing through voids experiences less gravitational distortion than light passing through dense regions. This affects lensing statistics and the apparent distribution of distant galaxies. Over large volumes, these effects average out, but locally they can matter. The integrated impact of voids on photon paths contributes to subtle correlations seen in background radiation and galaxy surveys. These signals carry information about expansion history and gravitational physics. There's also a deeper theoretical role. Voids are among the most linear structures in the universe. While dense regions evolve chaotically with complex feedback and nonlinear collapse, void interiors evolve smoothly. Their behavior can often be described with relatively simple equations. This makes voids valuable testbeds. If gravity or dark energy behaves differently from our current models, voids are where deviations are most likely to show up cleanly. Dense regions hide new physics behind astrophysical complexity. Voids expose it. In recent years, this has shifted how cosmologists think about emptiness. Voids are no longer just features to be catalogued, they are tools. They are used to constrain cosmological parameters, test gravity, and cross-check results from other probes. They also help resolve apparent tensions. When measurements disagree, one possibility is environmental bias. Voids provide a way to isolate that bias and understand how location affects observation. This doesn't mean voids explain all discrepancies, but they help rule out certain explanations. There's also a philosophical shift that comes with this view. For most of human history, emptiness was treated as nothingness. In cosmology, emptiness turns out to be structured, dynamic, and influential. The fact that most of the universe's volume contains very little matter is not a trivial detail. It is a defining feature. The largest voids push this idea to the extreme. They show us how far structure formation can go in the absence of sufficient mass. They mark the limits of what gravity can assemble. They preserve memory of the universe's initial conditions better than almost any other feature. And they hint at the universe's future. As expansion accelerates, voids will continue to grow. Dense regions will become increasingly isolated. Over unimaginable timescales, the universe will be dominated almost entirely by emptiness, with matter confined to rare islands. From that perspective, voids are not exceptions. They are the rule. The galaxies, stars, and planets we focus on are the anomalies. Temporary concentrations in a universe whose natural state is vast, expanding space with very little in it. The largest empty spaces in the universe are not cosmic accidents. They are the inevitable outcome of gravity acting in an expanding universe over billions of years. Understanding them doesn't just tell us where matter isn't. It tells us why the universe looks the way it does, how it got here, and where it's going next. Watch the next video.